Hello, hello. Okay, it's turn on off, turn off. Do you hear me well? Do you hear me clear? Okay, so we need to wait a bit. Oh, right now. Yeah, wonderful. So let's just wait a second. Because you know, most of the time I'm talking without the microphone and this is still fine. I'm quite a loud person and I'm walking around the stage, so I need to decide where is the good spot to be, because otherwise I will be just walking from one side of the room to the other. Okay, so probably it would be nice to have the line drawn here. Yeah, but, oh, wonderful, thank you very much. That will help for sure. Yeah, it's better to have a cage. It's good to know where are the boundaries of the cage.
You are safe.
Yeah, I'm safe now, and I will be in the spotlight, so that's the goal. Okay, should I start? It looks like somebody is giving me a Morse message. Please help. I'm enclosing that lamp. Okay, now I have my title screen. So it's probably time to start because we have just under the hour and a lot of slides. We'll see how many. So it's my pleasure to welcome you on the first session in the last day of the GeeCON. I hope a lot of you were on the party and you had a great time. I hope you liked the conference. And now my goal is to wake you up just right after the breakfast. And what we'll be talking about the truffle, about the part of the GraalVM, which is probably, like I mentioned in the abstract, the less understood and probably one of the most interesting. So my goal is to unveil a bit during that next hour what truffle is about, going step by step to build a context. So before that, let's introduce myself. My name is Artur Skowronski. I'm head of Java Kotlin development in the company called VirtusLab. And there is a slide. If you have any questions, there is a code. You probably know the drill after the 3 days. However, you can use that code. You can ask the question. We'll try to answer them after the presentation if you will still have time. OK. And now, I will go straight to the presentation. And I will start with a personal thing. I'm currently probably in the midlife crisis. And because, you know, I'm after the 30s, and currently I've started to think what is the next time, what I should do with my life. And you know what? I'm a bit disappointed, because I thought that when I will have midlife crisis, I will be focused on having the fastest car possible. That's not the truth. Also, I heard that developers and other engineers, well, mostly software engineers, are, when they start to have problems with their age, they are starting to doing a bit of tinkering. They start to have convoluted home assistant stuff and automating their homes. I'm doing that both, the truth is. However, that's not enough. Probably the most interesting from my perspective sign of being in the midlife crisis is that I exchanged Google for Google Scholar. Because when I started about 10 years ago, started to talk on the meetups, conferences, things like that, most of the time what I was doing, I was checking the documentation and then saying people what is inside. And that was quite boring. Currently, I'm checking academic papers and saying what's inside, and that is far more interesting. OK, and that's why today we'll be talking about the GraalVM. Who have ever used GraalVM? OK, so I see a lot of people. It's good to know that, because we are talking about, we are going a bit deeper than most of the GraalVM, most GraalVM talks mostly cover, because we are talking about this less introduced topics. Because what I tried to do, I tried to, even for myself, check what was in the original assumption of the project. What was original goal? What was what people who introduced the idea wanted to achieve? And the truth is, it is a bit different story than I expected. Because, GraalVM itself is a bit convoluted project. There's a lot of different components, and when I started to play with native image, things like that, it was hard for me to grasp what part is for what. Because, most of the time, whenever you are talking about GraalVM, you are talking about the native images. Native images is definitely ahead of time compiling, things like that. It's that part of GraalVM that is probably the most widely covered, especially in the recent time by creators of the GraalVM, because it's hard to it's hard for the community to not follow if even original creators of GraalVM are talking mostly about the native images. My goal is to cover those topics that are not that often introduced during the conferences, because if you want to hear about the ahead-of-time compilation, you probably should go to one of those sessions, because they will follow that in a bit more practical way. Me, myself, I will be talking about the truffle. And truffle, let me read it. This is the definition that you will find in the most presentation on the web page of the truffle, on the web page of GraalVM. Truffle is the language implementation framework, open source library for building tools and programming languages, implementations as interpreters of self-modifying abstract syntax trees. And most of the time, the whole story ends there. Nobody is giving more context about it, just simply the end, like with Lord of the Rings. You remember about Lord of the Rings. It has multiple endings, so I will go what is happening next, because after such a definition, I don't know anything. And the truth is, for years, even when I was already introduced to the GraalVM, I had no idea what truffle is even about. So I decided to go deep the rabbit hole, and now I'm sharing my insights. So during that presentation, we'll have more than 150 slides. It's about 45 minutes left, exact timing. So, like I said, at least I will try to wake you up, because I need to provide a lot of context to make our journey smooth. OK, so let's start from the beginning. And once again, I started with personal things about my age. I will go to the easier, younger times when I was learning to program. And probably the most popular book in Polish community when you start to program on the university or even outside of it is that book. Who have heard about it? OK, I see I have a lot of people from Poland. And you know what? You are lucky ones. Because you probably have introduced the far better word to the programming than myself. Because I'm from the Podkarpacie. Podkarpacie is on the east of Poland, close the border. It's place in the 90s when you don't have access to a resource like that, at least if there was no internet. I know a lot of speakers are far older than me. And I already heard during the speakers' dinner that, OK, I was learning from the BITEC. I was just rewriting basic, Visual Basic stuff on my Commodore 64. I was learning from Komputer Świat programowanie in C++. So it was a book bought in the grocery store on the rural area of Podkarpacie. And I love it with my heart. However, it skewed my perspective on programming a lot. Now it's time to introduce one of my most loved graphics of all time. I probably use it in the most of my presentation. It's one from the Byte.Go. Who have heard about the Byte.Go? Yeah, this is if you have never heard about it. And if you start looking for a job, I don't recommend it during times. In the current times, however, if you do, that's probably very good newsletter with resources about everything programming. And this diagram is especially useful for me because it presents 3 different approaches to the programming, to the compilation. And as you see, we have the simple one, the first one. When we have Go, we have C++, we have C. Whenever, this is exactly what I remember from my young age. I have a source code. The source code is compiled to the binary. I run binary. It's that simple. However, then I joined the Java bandwagon, and nothing was that clear anymore. Because, in Java, where you compile, you don't compile it in the same way I'm doing that in C++. I probably assume most of you know that. However, I need it for a story. I have a source code. You then compile it. there's a bytecode received. Now this bytecode is run on the virtual machine when we have yet another interpreted compilator, and then we have machine code. A bit convoluted. Most of the time I'm asking questions at this point. Why do we even have virtual machine? Why it need to be so complex? Okay, and most of the time I receive exactly that answers. Write once, run anywhere. Not important anymore from my perspective, because most of the time we know how our application will be run on production because we have Dockers, we have Terraforms, we have everything. We try to make our developer environment as close to production as possible. So probably write once, run anywhere is not that big case anymore. I'm sure that people from the GraalVM team will be talking about it later. However, there is one good point why it's worth to have a virtual machine. And now we'll start with our plain old JVM with very simplistic, presented in very simplistic way. Because like we already seen on the byte-by-go diagram, we have our JVM, which contains, our bytecode is first interpreted. However, this interpreted bytecode then goes to the just-in-time compiler, and finally the output of this piece is compiled code. It works in the way that, our application and our compilation process looks like that. We have a bit of source code. If there is Java C program, who have heard about the Java C? Because that's also not always the case. There's a whole generation of Java programmers who have never heard about the Java C. And that is quite interesting. I don't always have all the hands up. So you're compiling to the Java C, and what you are receiving is not the machine code. What we are receiving is a bytecode. As you see, the list of instructions that are then interpreted line by line through the interpreter. And this is quite fast. The truth is that interpreting in Java is quite fast. However, it's slow in comparison to the standard compilate machine, very optimized code. So what our Java application is, what the Java virtual machine is doing, what JIT, just-in-time compiler, is doing, it's taking them it's checking how the functions are run on the production, it's checking where it's used, it's selecting the hotspot, so the pieces that are mostly used most of the time, and it's optimizing them to the machine code. Everything is probably clear. I'm sure nearly everybody here heard about, at least most of you heard about this process. However, it's just the start, because we need to go deeper. And as I already made the Christopher Nolan reference, I will make another one. Have you seen the Prestige movie? Yeah, and this will be a bit spoiler. I'm sure just the people who have seen the movie will know what I'm talking about. However, I'm quite proud from this reference because, Java compiler don't have, Java virtual machines do not have just one JIT compiler. It has two. And it has two. So that, I'm done with my Prestige reference there. Sorry for the spoiler. However, right now, like you see, it's a bit more complex. Why do we even have two just-in-time compilers? We'll start with the first one. The first one is called C1, and it's client compiler. The client compiler, also known as a C1, is a type of JIT compiler optimized for faster startup times. It strives to optimize and compile code as quickly as possible. And what's the goal of the C1? As you see there, it's just compiling our bytecode into machine code as soon as possible. What does it mean? We probably don't want to waste resources on very deep optimization because we want to do it fast because we want to make our application fast from the startup. And as we are running the code in the virtual machine, we already know what architecture we are using, so we are optimizing our code in the basic way. However, the basic word is important here because we have yet another compiler. It's called C2, and it's server compiler. And what it's doing? It's doing the optimization based on the real usage of program. It observes, analyzes the code for a longer period of comparison to C1. This allows C2 to make better optimization in the compiled code. And that's the true reason why even today it's worth to have virtual machine. Because once again, we need to go a bit deeper. Because what C2 is truly doing, it's doing dynamic optimization. A JIT compiler can recompile parts of the code base during the program execution thanks to profiling. And how this profiling looks like in practice. In practice, it looks like, OK, we have our code. Probably it should be in English. Nasz code is our code. This code is going to the interpreter. Interpreter starts to see how the given application is run on the practice. Code is going to the C1. C1 is doing first optimization of the code, and that is put in the code cache. And after the longer period of time, when our program already is used and our methods are already used in the multiple contexts, C2 is starting to optimize them a bit more. It's done through the process of so-called speculative optimization. Speculative optimization. OK, have you heard about the meltdown and Spectre? Have you been there during that time in the industry when we learned that, OK, the CPUs has a major flaw that will just make them at 20% slower or something like that? Why was that? It was because what processors are doing, so what CPUs are doing, due to fact that currently they want to optimize instructions as fast as possible, make them as efficient as possible. Sometimes they are guessing how our programs will look like, how they will behave like, doing some called blanche prediction. OK, it's sometimes better to just go one specific path, and if we will be wrong, the optimizer make a step back. Clever hackers started to use it to steal data, so unfortunately, it's not always the best idea. However, the bit similar thing is done in the optimization of the Java code. OK, here we have the simple sample of the Java code. Like you see, first we have interface, this number adder. It adds two random numbers, and it has two implementations. The first is simple adder, and the second one is logging adder. They differ in the one way because the logging adder log a bit of information. However, our application, to make everything as smooth, as fast as possible, whatever JIT is seeing, OK, let's look on this code. As we see, this method is used in a way that we have simple adder chosen as our basic implementation, and we are running it in the loop multiple times. And what our machine see? It sees that that given piece of instruction, that given implementation is always used. So probably paying the cost of abstraction, because every abstraction has a cost, is not worth anymore. Because we have seen 1,000 times that, OK, it was always standard number adder used. And JIT compiler is optimizing that code to use to just get rid of abstraction. However, unfortunately, somebody is joking there and making instruction that after the 5,000 instruction, it will be logging adder used. So we are changing the implementation. Unfortunately, what needs to happen? Our code needs to be de-optimized. De-optimized because, OK, we optimize it in the way that it will get rid of abstraction, will always use the direct reference to the given class. It's not the case because we have seen on the production that rules change, so we need to de-optimize. That's how tiered compilation works in the practice. OK, that was introduction, and it was complex, wasn't it? A bit. Probably most of you have heard about it. However, it is very hard to implement, especially as we are seeing that our virtual machine is written in the C++, and C++ developers are the dying breed. So I have heard during the podcast that of Adam Bien with the Thomas Muttinger from the GraalVM team that the problem is that, for example, if somebody is joining the JVM team, virtual machine, he is getting productive and can do any changes after half a year because it's such a messy, such a hard-to-grasp code base. That's why there is not the JIT compilers are not they are not introducing a lot of changes between the versions because it's really hard and the process is quite complex. That's why GraalVM is that interesting project. Because GraalVM, and this is description as a directory from the web page of the GraalVM. GraalVM is a high-performance JDK distribution that compiles your Java application ahead of time into standalone binaries. Those binaries start instantly, provide peak performance with no warm-up, and use fewer resources. And that exact definition is what we are looking for when we want to have a native image. So even the main definition that you will find on the GraalVM is focusing mostly on the native image capabilities. Let's get back to the mentioned paper. In that mentioned paper, in the original one, that was one VM to rule them all, so once again, Lord of the Rings reference, the project was described a bit different. Their goal was to create a virtual machine that will just have all that will allow to implement a lot of different languages because they will be using a bit different structure than the bytecode. They will be using the abstract syntax tree. And that was original goal of the GraalVM. Create one virtual machine that will just allow all those languages do not re-implement that highly complex logic of the just-in-time compilers and how Java was done it to make the language blazing fast. Because Java's just-in-time compiled code for Java is very, very fast. In the comparison, for example, to the languages like we'll see on the list, they already mentioned it. Complex, like PHP, Python, Ruby, R, things like that. They even mentioned that JavaScript was made fast in the period when already we had a lot of developers who were doing that exact code in the JavaScript, so they started to implement interesting features to the JavaScript virtual machine, and we'll be talking about them a bit later also. One virtual machine to rule them all. The fact is that it's not that original idea, because already on the JVM we are able to run more than one programming language. We are able to run Kotlin, Scala, Groovy, and the others, because we have Ceylon, we have Frege. Do I have any Frege developer in the room? Have you heard about the Frege? It's Haskell on the JVM. Because Scala is not a Haskell on the JVM, you can go deeper. Yeah. That's the reason why I sometimes call Kotlin or Scala the syntax sugar over Java bytecode. Those language developers do not like it a lot. Yeah, so especially Scala ones. So GraalVM, it's a similar idea, because it's idea, if we can have multiple languages run on the Java virtual machine, probably we can create a virtual machine that will allow us to run even more languages, like Java, Ruby, Python, C, R, Scala, Groovy once again, R, JavaScript, C++, currently also WebAssembly, so a lot more. Also, they wanted to make it portable, so it can be run as the OpenJDK, it can be dropped in replacement for Node.js, it can be embedded in the Oracle database, and that's probably one of the most interesting cases of the GraalVM, because I don't know if you heard that the GraalVM runtime is embedded into Oracle database to allow running of the JavaScript-based database triggers. It's a bit of a crossover episode. Recently, it was also introduced for your MySQL. It's also allow us to create the standalone version of the binaries. So, like you see, a lot of different options. Something that wasn't previously possible on just standard JVM. And to achieve that, GraalVM has quite convoluted architecture. That's why whenever somebody is talking about the GraalVM, you should ask which one, because the truth is, there is no one GraalVM. The project is so complex that there's no one GraalVM. There's no it is GraalVM. I don't want to provide a wrong idea there. There is one GraalVM, however, it can be run in 3 different modes. So we need to describe all of them. The first one is standard GraalVM as just-in-time compilation mode. So what GraalVM as a JDK is doing, it's quite simple. It's simple in the way that we previously had thus 2 just-in-time compilers, C1 and C2. And if we run GraalVM as our JDK of choice, we simply have a different implementation of just-in-time compiler. It's GraalVM compiler, so-called Graal compiler. Because it's not GraalVM compiler, it's Graal compiler. It's called like that. what it's doing in a different way, it's that, as you see, original hotspot compiler, hotspot virtual machine, our C1, C2, what we're doing, they were doing just-in-time compilation in the way that bytecode was interpreted, and then we have this optimization, the optimization profiling, complex process. In the GraalVM, it's run in a different way, because GraalVM, Graal compiler, is taking bytecode as the input and replacing it, creating the intermediary representation that is Graal3, Graal intermediary representation, and it's optimizing it in much different way, much more similar to what is happening in the JavaScript engines or more dynamic programming languages. And the fact is that, like I said, it's a replacement for the, our C1, C2 compilers. It just allows us to create the, it's like it's described in the object. GraalCom evaluates the constant objects when it parts the bytecode and represents those as a concrete Java objects to analyze. Hence, the Graal intermediate representation gives a more concrete and easier to use representation of the analyzed code than the bytecode. It's just taking bytecode and replace it to the Java graph. And for the Java developers, it's far easier to play with that stuff than having just work in the basic bytecode. It was interesting because, you know, like I already mentioned, you can just use GraalVM as a standard JDK. So you can just take it as one of the possible implementation. Currently there's multiple implementation. One of them is just GraalVM. And during the time of the JDK night, there was even introduced something that is called JVM compiler interface. Who have heard about it? Yeah. So this was the project that, okay, if we have problems or we want to have different approaches to C1 and C2, probably we should introduce a way to plug something external to our Java virtual machine. And Java compiler interface allowed to that, and soon it was followed by ahead-of-time compilation spec for Java. It was next followed with the experimental Java-based JIT compiler based on the Graal. So Graal was possible to be just, it was added to the JDK distribution and was possible to just using the specific flag to start run our application with the Graal compiler. Because that interface was used for that, and it was removed in the JDK 17. Because, you know, just by fact that it was external to the virtual machines at this stage, it was pretty slow, and all the gains were lost. Fortunately, currently there is a second approach to the topic, Galahad project. I love the name because you know who Galahad was? Galahad was that Camelot knight who brought the, due to myth, Graal to the King Artur. So I love the reference, it's very fun. So we currently wait for the Graal compiler to once again be reintroduced to the JDK, just in the faster, more efficient way. So this is our standard, the first mode. This was the mode when we used GraalVM as a JDK. Now let's focus on the other approach, so ahead-of-time compilation. Because, like I already mentioned, and this will be quick because, like I said, there are sessions about that. Like I mentioned, Graal compiler is external component that is external to the Java virtual machine. C1 and C2 is just part of the code base. Graal compiler is external. And what does it mean in practice? In practice, that means that we can just run it outside of the context of the virtual machine. And this is ahead-of-time compilation. So you are just taking off code. You are running Graal compiler, which you compile Java code to the machine code. And then it's run on something that is called substrate VM, which is thin version of the virtual machine, which all the not necessary parts were removed. And by not necessary parts, we are seeing, okay, substrate VM is low footprint, fast startup, embeddable virtual machine, foreign written in a subset of Java. So it was written in Java. It serves as an implementation basis for hybrid memory management technique. What does it mean in practice? Why it's the just the part, they have a part of the functionalities of the Java virtual machine. Because subset VM is working under something that's called closed for assumption, and it means that class loader, it's hard to use any dynamic features of Java, because it do not have class path. That means that it's hard to load class using method handle, proxy, or even standard reflection. Due to popular myth, it's not impossible. However, it's much harder. Probably, like I said, I won't focus on this topic because it's outside of the scope of this presentation. I assume I haven't seen the presentation. On the 2 p.m., you will be able to learn a lot more how to make it work in practice. But like I said, it's not the scope of this presentation. I just wanted to put it there for the reference reasons, because now, finally, we'll be able to talk about the truffle, because we are already more than halfway the presentation, and truffle was mentioned during the introduction. So let's start about the truffle. There was something that was pretty important in the original paper that was not mentioned, that was not often mentioned in the context of the GraalVM. All those languages, PHP, Python, Ruby, R, Perl, MATLAB, they are languages that are dynamic. And that's the reason why it was so hard to implement them on the Java virtual machine, standard one. Because Java virtual machine is not suitable for the dynamic languages. It's working on the different basis, because if you want to introduce, because dynamic languages are working in a bit different way than the static ones. And probably the good definition of truffle, the easy to grasp one, I will use the one from the truffle closure as self-optimizing as the implementation for closure. So somebody's master thesis. Yeah, whenever I learn that people are doing their own implementation of closure as the master thesis, I feel bad with myself, unfortunately. However, I've liked this piece because it provides very digestible introduction to what truffle languages are. The truffle framework was designed for a high-performance implementation for languages with the dynamic type system. As a consequence, the closure programming language could also benefit from optimization performed by truffle-based interpreters. And now we are getting to the point, because truffle was made for dynamic languages. And due to the reason, as we introduced yet another term, we need to go sidetrack once again. Because now we'll be talking about the dynamic and static typing. You probably have seen a lot of memes like that. And you know what? I hate those, because they are missing the point a lot. Because there is not direct conflict between the dynamic and static typing. They are working, they are solution to the much different problems. And I will try to unveil that. Because typing itself is solution to the... OK, I have a question there. How can we prove that this program works? We have something like that. Do you have any idea? Execute them. You need to prove. OK, you can. If you execute, you are checking. OK, that set of input is working fine. But are you able to? Are you sure that it will be working for a different kind of the inputs? Probably not. And I was looking for the brave ones to say, OK, you can, because in 1957, there was so-called Rice theorem published, which is proving that every non-trivial property of recursively enumerable languages is undecidable. In practice, that means you cannot prove that program works, unfortunately. However, for some reasons, we are pretty sure programming, and we are pretty sure that everything will be working fine. Because we, as engineers, found some quite interesting techniques to resolve that problem. And one of those is static typings. Because if we can just prove that program is working, probably we can just decide, we can just agree on the set of rules that we need to follow when we write our programs. And if we follow them, the computer will be able to check if everything is fine. And the first language that introduced something like that, as far as I know, is Fortran, where you have seen, Fortran introduced something that now we call type labels. So now we agree, we are saying our program, that that a variable is integer, so it's number. If we'll use it in the outside of the number context, please let me know that I just kick myself in the foot, in the knee. And what static typing is doing, it introduced lower bound of correctness. It do not prove that program works. It proves that if type checker is going through all the structure of the program properly, it means that, fortunately, we get rid of the set of the, we are fine with the set of rules we agreed upon, and now we'll be able to run our program. That's something. This is the set of rules that was checked. Maybe there are some different errors because it's possible to have a program that will go to the type checking and will still fail in the production. As you see here, okay, we have our generics in Java. There is a list of integers now, and we are filling it with integers. Now we are replacing using just assigning it to the list without the parameterized type. Now we can add everything there. And still, our program will be working because, okay, it's passing the set of the constraints, set of the rules that we agree. It doesn't mean it will be working fine in the production because we can still, if we just do something that clever in our code, probably something will break. However, we just agreed, okay, that's outside of the scope of our type checker. Our type system is not robust enough to find that. And that was static typing. Dynamic typing is a lot different problem because dynamic typing is something like that, but in runtime. Because you know what? Whenever we have our function, we have our variable. That variable, it's not just a value. It's dynamic. Whenever we have dynamic type system, we have it's container. It's value and a type. And in practice, it means that as we have additional information about the type of our variable, we can do some basic checks in our application program. So, for example, we are able to confirm that, okay, we are doing the absolute on the integer. That's totally fine. On the other case, we have string trim on our application, on our int. Probably it's something wrong there. You are doing some wrong logic. So now we are having runtime exception. And that's a good thing, because most of the time, you want to have exception, not a wrong behavior in your program. At least if you are not JavaScript developer. So it works like that. However, as you see, if every time you use our variable, you need to do some basic checks, you have performance overhead. And of course, it's optimized in some way by the dynamic systems virtual machines. They introduce 3 terms. Our function, which do not have any types because it's dynamic in that situation. X can have have information about its type. However, our function do not have any information what X can be. They introduce some interesting terms because it can be monomorphic, it can be polymorphic usage. So monomorphic we have always used in the same way. Polymorphic, okay, there are different multiple implementation, and there's third term that's called megamorphic. So okay, monomorphism in the context of dynamic typing engine optimization refers to a situation where a function is consistently called with the argument of the same types. And there is the blessing situation, because if the function is always run with the exact type of the parameters, virtual machine, due to profiling, can optimize it. Optimize that function, so they always assume it will be that given type. It's not worth checking anymore. Other thing is if we have more complex situations. So for example, polymorphism. A function is called with the argument of different types. This requires the engine to handle multiple cases and can lead to less efficient code. Because, okay, there will be if somewhere. Because we need to branch logic to a different path. And there is third type, is megamorphism. It means that we cannot optimize anything because it can be everything can be put in a given function. So it's not worth to even try to have more specialized implementation of our function in the runtime. Okay, and having that logic in mind, now we are able to get once again to the truffle. And whenever GraalVM is running in the truffle mode, it uses something that is called language interpreter. So language interpreter is just a piece of program that is run over the GraalVM compiler, over the Graal compiler. And those kind of programs are written in the framework called Truffle. Finally, we got there. As you see, how it works in practice, our code, we have information that our method is called add, and we need to create some generic implementation, because always there need to be some generic usage, because we have dynamic program. Everything can be used as the argument. However, if we know that our method will be used in some specific types, we can just design particular specializations. As you see, one for the integer, one for the double. In this case, original paper, it contains quite complex trees there, and we'll back to it. It's because what Truffle is using inside this abstract syntax tree, it's a concept taken from the JavaScript and dynamic programs optimization, because you know. Thomas Wurtinger, the guy who was creating GraalVM, I've learned that he was intern in the V8 team, so we can assume that a lot of ideas, and it's even mentioned in the paper, was taken from the JavaScript, so thank you, JavaScript, for that. And one other source of the inspiration was PyPy. So Python programming, Python interpreter written in Python. The partial evaluation term was taken from that language. Okay, so let's start seeing how it works in practice. On the left side, we have a standard tree of our program with our add method in the situation. First, we have each node of that program in an uninitialized state. And here on the right, we have transition tree. So we can see that from state that is uninitialized, we can go to the integer. We can go to double, we can go to string, and if, for example, we don't have particular implementation from the integer, we can use implementation on double, because they're compatible with each other. Integer can be used in the double context there. So how this transition is going? Okay, if we do not know, at the beginning, we do not know how our program works, because it's not profiled yet. So what we are doing here, we are making a generic case that it's not have any optimization at all. However, as we are going through our application logic, and more, we are getting, our abstract syntax tree profiling that is included in Truffle is learning about how particular branch of the trees are used in the production. So, okay, we can see that somebody quite, I would say, tidy is using that exactly method in production. So always, if we are adding two numbers, they are not putting the unstructured objects there. So probably the right tree, right usage, right place when we are using add method, it can be just made performant, efficient for the integers operation. On the left side, we're seeing, okay, that method, in that case, are using strings. So, okay, we can probably, if it's always using strings, we can optimize it properly. And what is interesting in the Truffle and its optimization, each usage of method is optimized in a different way. So you can have the same method can be used in different places and be optimized differently. That's pretty important for the dynamic languages. And as we see, okay, we have in our integer right tree, there is the first time when we started to use double. So, okay, probably as we have used double in the one use case, probably we cannot anymore just have integer specialized tree. However, we can go with the double one, because double and integer are they're compatible with each other. And fortunately, it's still better than using the generic case. However, if we, for example, on the string tree have object as the argument, probably not worth to optimize a lot, because everything can be there, and we are getting back to the generic use case. Let's assume this left tree of strings was still there. There was always strings, so we have two stable optimization, one for the integers, one for the doubles, one for the strings, and for the longer period of program running, they were stable. There was no mistake. They were always used like that. So now it's time for the optimization. Because if you see that always our program was always used with a particular type, we can make each of the branches here monomorphic. Once again, through the speculative optimization, because we are not sure that after the week of program running on the production, there won't be any change in how the method will be used. However, after the period of running in stable way, we can probably assume that. So first thing that it's done is adding the guard nodes. I don't know why it's there. There should be just instance of checking. Okay, on the left side we are just checking if there's always string. On the right side we are checking that there's always double. So we have check on the instance of things like that. And after that we are putting our already optimized truffle abstract tree to the Graal compiler. As Graal compiler, as it's already working on it's able to optimize, as this is already a Java implemented abstract syntax tree, Graal compiler can optimize it through the process called the partial evaluation. Partial evaluation is a key optimization technique where the Truffle framework precomputes parts of the program based on known inputs and constant values at the compile time. This result is highly optimized machine code for guest languages, significantly improving the performance of the languages. So what it's doing, it's compiling our tree. Our tree is no longer dynamic. Now it's just merged together and in the very efficient implementation that is close to the machine code. Unfortunately, after the period of time, it's possible that some clever developer will just start adding some objects to each other. Unfortunately, in a situation like that, we need to do the optimization. What's fortunate that Truffle compiler is prepared for that, Truffle language interpreter is prepared for that, and if it's the optimizing one branch and one use of method, it's the optimizing only that method. All other parts of the optimization, optimized engine, optimized tree, it's still there. Okay. So we have a theory, we have 5 minutes. All right, so how do we put this into practice? In practice, it means that our language interpreter can just run we can just implement language interpreters. And for years, Truffle was we needed to use the GU application to download Truffle languages. Currently, they are, through the process called Truffle Unchained, it was a big announcement last year in the GraalVM community, they are currently distributed as a standard Maven library that can be taken from the Maven Central. And it works in that way, that, okay, we have our application, as you see on the right, we are saying that, okay, this piece of code, it should be evaluated in the context of the JavaScript, and we can do any operation of that particular language in the efficient way, because Truffle, after some period of time, will start to optimize exactly that. Also, what you achieve the interoperability, because you can put anything from the Java here, to the Truffle runtime, and you take anything from the Truffle runtime to the Java application. So through the Java glue, you are able to just join together Ruby, JavaScript, things like that, and have one runtime that is able to compile code from the multiple different languages in an efficient way. Quite interesting one. However, probably my most interesting piece is the fact that you can use it for even more clever stuff. Because we Java developers are joking that Python developers, most of the time, they are just wrapper over the C++ libraries. In the machine learning, it works exactly like that. However, the truth is, it's exactly the same with Java, because the Java virtual machine is written in the C++. So we are also riding on the C++ back. However, there was a lot of different approaches to change that in practice in past. One of them was the Maxi virtual machine that was planned to introduce the Java virtual machine in the Java. However, we can do it's not there. Maxine was dropped. It followed the Java. The fact is, GraalVM is the successor of the Maxine machine. However, there's one very interesting stuff that is coming from that kind of initiatives. It's Espresso, which called this meta-circular compiler. And what does it mean in practice? As you remember, GraalVM is quite complex idea because we can run just use the GraalVM, it should be GraalGit compiler, and run standard Java application on it. We are able to add the truffle layer, so write dynamic languages interpreters on the truffle. However, that means that as the truffle interpreter is just the standard library that can be taken from the Maven Central, you are able to run the Ruby code in the context of Java 8 as a library. Clever. However, there is yet another project. The project is called Expresso. And goal of the Expresso was to implement Java as a truffle language. And what does it mean in practice? What it gives us? It gives us a quite clever approach that, because as you see, every truffle library can be run on the truffle interpreter can be run on the in a standard Java application. So as you see, Expresso can be run on the Graal compiler, and there is much more efficient. It also can be run on the standard C1, C2 compiler. So in practice, it means that we can currently run Java runtime as Expresso library for JDK 11 on JDK 8. So we can just run Java runtime on the Java runtime, run Java runtime on the Java runtime. Of course, there are caveats for that, because performance is 2 to 3 times slower than hotspot in the GraalVM mode. If you are running into the GraalVM. If you are not running on the GraalVM, it's even slower and possible only for Linux. So it's not that clever trick as possible. Most of the time, it's mostly used for running the Java bytecode, not create code in the strings, because Java do not work that way. It's not dynamic language, so it's very hard to just patch pieces of code together to create a Java application. However, there was quite initial success. I'm ending here, so I will be able to wrap it in a minute. So one of those is native JShell. So we are, for example, introduced JShell that was introduced in the JDK 9 to run on the Java 8 through Truffle. So that's one of the most interesting use cases of Truffle. However, I have one more for you. Do I have anybody who is just running JDK 8 on the production and cannot go further? Okay, you are lucky guys, because if you are not, I have idea for you. Because you can use Truffle to run in any JDK 11 optimized code on the Java JDK 8 runtime. And that's probably the evilest thing a Java programmer can do. I love the idea. And that wraps up our presentation. I hope you like it. And now, if you like such, I would say, digging deep into different new ideas that are coming to the JVM world, I just suggest you to subscribe to my newsletter, because I'm doing such a journey each week, describing what's interesting happening in the JVM world. And now it's time for questions. Thank you very much. Let's see if I have any. Okay, Thomas Brittinger was not just intern in Google, he actually wrote a job optimizing VM compiler called Crankshaft. Okay, that's true. That's what I heard. He was probably it's what he have said about himself in the Adam Beam podcast when I heard, so probably he was just underselling what he has done. Okay. Do I have any more questions? If not, thank you very much, and see you on the next session.